Hey guys, welcome back. Day 41. We're going to talk about enthalpy. And so we are in the chapter where we're talking about heat and heat to work and heat transfer and how do we measure heat transfer. Remember work. Work is negative P dV, right? Or work is force times distance. So if we recall here that work requires a coherent or concerted motion of the particles in the system, such as an expansion of the system, like a piston in a car engine. So when the piston is driven, most of the cases, I believe they're driven down, the the volume of gas in the cylinder expands, and that expansion drives that piston down, and that's how the work is done. It's very organized motion. If the piston doesn't move, then the obviously the car engine doesn't do any work. So let's write that down. If the system does not expand, then no work is done. Delta V equals 0. So if delta V up here equals 0, 0 times negative P is 0. No work. Therefore, any change in E, which if you remember is the internal energy of the system, is due only to Q, which is, of course, heat. Delta E then equals Q. So the change in internal energy equals the heat. Or sometimes we'll write delta E equals QB to indicate constant volume. And that makes sense. So if my pistons, the car engine is not on, the pistons aren't moving in the car engine, there's no work being done. I can't drive. We get that. So as long as the pistons are moving, we have a potential to do some work. And if we have no volume change, no work done, it's just the energy change in this internal energy change is equal to the Q. When we talk about lab experiments now, it's a little bit different than a car engine. In lab, in many cases, the volume is not constant. And work is done. So if you're mixing two liquids or you're dissolving something, the volume changes. It happens. It can happen. So what happens? Well, on Earth, most of our labs are within 3 hours that we'll do, especially in Chem 1. And that's this audience. In Chem 1, if your lab is less than 3 hours, chances are the pressure of the atmosphere is not changing drastically, hardly at all. Does it change from day to day? And yes, but it's probably not going to change that much in 3 hours. So if the pressure is constant, as is often the case in lab experiments, especially shorter ones, then work done is W equals P dV. However, it's a negative, right? W equals negative P dV because an increase in volume means that the system is doing work on the surroundings. And the internal energy of the system decreases. We go back to delta E is Q plus W. Heat plus the work. The change in internal energy of a system is equal to the heat and the work. Well, if we substitute for work, delta E is equal to Q, the heat, minus P dV for the work. And we can write QP for constant pressure. Rearranging, bringing P dV to either side, QP equals delta E plus P dV. And Q, honestly, we can measure. That's pretty easy to measure. Thermometers, we have very good thermometers. P dV can be difficult to determine. So we're going to define a new function called enthalpy. And that'll be H is the symbol. So delta H, the change in enthalpy, would equal QP, the heat transfer at constant pressure, which is equal to delta E plus PdV, the work. So enthalpy means heat inside or heat content. Delta H, change in enthalpy, is the heat gained or lost by a system at constant pressure. So we incorporate work done. Now note, delta H and delta E, right, with these two. So a little delta H and delta E, these two. The difference between delta E and delta H is small for reactions that do not involve a change in gas volume. So they're very similar. So delta E and delta H will be a very similar size unless you have gases. Let's look at the two processes, if I can gain heat or if I can lose heat. Okay, so if heat's coming out or heat's going in. A lot of times we'll start with exothermic for heat out. Versus endothermic for heat in, right? Exo's heat out, endo's heat in. Two little XY axes here. On the X, I have the reaction. Oh, she's black. As the reaction proceeds. And the Y-axis will be H. For an exothermic reaction, a lot of times my reactants have more heat content than my products. And so delta H is negative. Conversely, endothermic, my reactants have less energy than my products. And the change in enthalpy would be delta H positive. So examples. What's an actual example? Well, if I have hydrogen gas, this one have O2 gas going to H2O liquid, that'll produce 242 kilojoules. So delta H, in this case, is negative 242 kilojoules. We know when hydrogen and oxygen get together and make water, vapor, 242 kilojoules is released. Another reaction would be if I add 90 kilojoules to 1/2 of nitrogen gas plus 1/2 mole of oxygen gas, I would go to nitrogen monoxide gas, and that delta H requires 90 kilojoules per 1 mole reaction. So those are two examples where heat is required for the reaction to go in endothermic, and heat is released. So there's the two qualitative diagrams of delta H with endo and exothermic. The question then becomes, how do we calculate this delta H? There's three ways. First way is Hess's law. Hess's law basically says the heat of a reaction which is delta H RXN, heat of reaction is independent of the route taken. Between reactants and products. Enthalpy is a state function. Kind of like flying. We care about the destination and the departure. A lot of us, if we have to make an extra stop to save money, we'll do that as long as it fits into our criteria of time and date for destination and time and date of departure. Some of us won't. Some people will pay more to just go one up, one down. It just depends on what your options are. That's kind of a good analogy for Hess's Law. So it doesn't matter what we're doing, how we do it. We just know the state of the reactants, state of the products, changes the change. Here's a Hess's Law example. What's the enthalpy change, delta H, for this reaction? You have CO plus 1/2 O2 going to CO2. What's delta H? And you have to manipulate these equations, and those are the two equations. What I like to do, this is very similar to elimination in math class. Is reactants react to our higher green CO2, 1/2 O2, and products are produced, CO2. And so I highlight below, carbon's not involved, O2. I have CO, right there's 1/2 O2, there's a reactant, CO2 is a product. So it looks like where we have to flip the first one. If I flip the reaction, delta H changes sign. Flips sign. I can also double reactions, half reactions, triple reactions. If I double the reaction, I double delta H. So whatever I do the reaction, I do delta H. So in this case, I flip the reaction, I reverse equation 1, and then I can just keep equation 2. So if I reverse equation 1, I would get CO gas plus 1/2 O2 gas going to carbon solid plus O2 gas, and now delta H is positive 110 kilojoules. Keep equation 2, carbon solid plus O2 gas going to CO2 gas. Oh, that's a highlighter. And we keep this delta H the same at negative 394 kilojoules. If we add up these two reactions, what do we get? Well, the black ink is gone. I get the green and the blue. CO gas plus 1/2 O2 gas going to CO2 gas. And that's what we want. Delta H, all I have to do is add these up. And that would be what? Negative 384? I'm sorry, 284 kilojoules. And that's Hess's Law. That's all it is. Another example, 82. Calculate delta H for that reaction. Well, go back to my highlighter here. CH4 and Cl2. And carbon tetrachloride and hydrochloric acid. And the coefficients really matter. If I look, I got CCl4 is there, HCl is there, we have CH4 is there, Cl2, and Cl2. Okay. Well, what do we need to do here? Well, I get the first one, it looks like I need to flip. For reactions, so reactions 1, 2, and 3. 1, it looks like I got to flip. because the green's on the other side. The green and it just needs to be on the other side. There's nothing else. Second one, I don't know. Third one, I don't know. Well, if I look at the second one, if I add up second and third, I get 3 Cl2s. That's not good. If I add up second and third, I get 2 HCl, which was not good. CCl4 has the same coefficient of 1 and 1. So I'm thinking I'm going to keep equation 2. And equation 3, if I double that one, will I get what I want? So let's rewrite these. Equation 1, I have CH4 going to CS plus 2H2 gas. So now delta H is positive 74.6 kilojoules. Equation 2, keeping it. Carbon solid plus 2Cl2 gas, giving me CCl4 gas. And equation number 3, I'm doubling it. 2H2 gas plus 2Cl2 gas going to 4HCl gas. So delta H is, oh, and I forgot equation 2. Equation 2 we kept, so that's still negative 95.7 kilojoules. And then 2 times 92.3, so that's negative 184.6 kilojoules. Does this work if we are going to cancel? What cancels here? Well, the carbons do. What else? The 2 H2s do. I think that's it. And if we write out, I had CH4 gas plus 4 Cl2 gas, giving us CCl4 and 4 HCl. And that's exactly what I wanted. So then we just add up our delta H's here. Negative 205.7 kilojoules is what I get for delta H. That's Hess's law. That's all we're doing, is basically the elimination in chemistry. So we're just taking reactions and manipulating them, adding them up to get what we want. The second way to calculate delta H is standard enthalpies of formation. That's the example. There we go. And the standard enthalpy of formation is going to be written as, we got delta H. There's an F for formation, and a degree sign for standard. That's the standard state. And that's usually 1 atmosphere, 25 degrees Celsius, sometimes 20 to 25 degrees Celsius, but 25 degrees Celsius for us, and 1 molar for solutions. That's our thermodynamic standard state. The definition is the standard molar enthalpy, sometimes referred to as heat, of formation of a substance is the heat released or absorbed when 1 mole of the substance in its standard state is made from its constituent elements in their standard states. So that's what delta HF standard means. Now, by definition, an element in its standard state must have a standard molar enthalpy equal to 0. Delta HF standard equals 0. What do I mean? So if I look up delta H standard formation of oxygen gas, let's say, that'll be 0. That's just what's going to happen. Because that's how it's made. That's how it's created. There is no creation of oxygen gas anymore. It's there. It's already been created. For calculations, we have the standard enthalpy change for a reaction is equal to the sum, and this is a Greek letter sigma for sum, of the standard enthalpy changes of the products minus the sum, the standard enthalpies of formation of the reactants. So it's products minus reactants. That is how we're going to calculate reactions with this way. So this is the second way. The first way is Hess's law. This is the second way. Products minus reactants with the standard enthalpies of formation, delta HF standard. And here is the example. How much energy is released when methane burns? And it gives you delta HF in purple here. And there's nothing under O2. Is that an accident? Is that a typo? No. Because if we go back, elements by themselves are 0. So Fe, Hg liquid, O2 gas. Now O2 liquid would not have a delta HF equal to 0 because oxygen is not a liquid. Oxygen is a gas. Carbon solid. You have, gold metal. But liquid gold has a delta HF because you have to add heat to gold to melt it. That makes sense. So how do we do this? Well, delta H of our reaction is equal to the sum, the standard enthalpies of formation of products, minus the sum of the standard enthalpies of formation of the reactants. Delta H standard equals our reaction. Products, CO2 plus 2H2O. Reactants, minus CH4 plus 2O2. Delta H, standard of our reaction. I'm just going to put in our numbers. We use purple here, so this is negative 394 kilojoules and negative 286 kilojoules. We had negative 75 kilojoules and 0 kilojoules. Doing this math, I get a delta H of the reaction equal to negative 891 kilojoules per 1 mole of reaction. And this is a heat of combustion. the second way to calculate delta H. The third way to calculate delta H is by calculating enthalpy with bond dissociation energy, making and breaking bonds. We know when a bond is formed, energy is released, which is an exothermic process. When a bond is broken, energy is required. And this is an endothermic process. This means we can approximate delta H of a reaction is equal to the energy of bonds broken minus the energy of bonds formed. That's how we can approximate delta H of this reaction. So we're going to calculate the heat of formation of hydrazine. Well, element at standard state, and so let's just say that's a gas, because what do we got? Well, Lewis structure-wise, N2, H2, and then N2H4. Well, N2 has 10 electrons, so it's 2, 4, 6, 8, 10. Hydrogen has just the one bond, one electron each for a total of 2 electrons. N2H4, what's going to happen here? Well, chances are we have an N-N bond because there's an N-N single bond there. So let's say that the N's are bonded to each other. And then we'll have an H on each N. Let's see if that works. Does that work? 2, 4, 6, 8, 10, 12, 14. Is that, yes, 14 electrons is what we have. So what bonds are broken and what bonds are formed? Broken would be, it looks like the N triple bond N and the HH are broken. Formed would be all those. So I would definitely break the whole triple bond and then make the single bond. I would definitely do that. Delta H of my reaction will equal the energy of bonds broken minus the energy of bonds formed. Delta H of my reaction will equal bonds broken. Well, it looks like I have NN triple bond, and I have 2, because there's a 2 here, 2 HH. Bonds formed. Looks like I have 1 NN and 1, 2, 3, 4 NH. So there are my bonds broken minus my bonds formed. Now we got to plug in some numbers. Delta H of my reaction equal to NN was 946 kilojoules per mole. 2 times HH 436. Minus NN would be 159. Hopefully we picked up that the single bond is much weaker than the triple bond. In fact, it's more than 3 times stronger than the single bond. The triple bond is. Pretty impressive. Plus 4 times NH is 389. At this point, it's all algebra. Now, if you want to, you can break this down, delta H for the reaction equals, you can break it down, in this case it's pink and purple, but bonds broken minus bonds formed. If I break it down, I get 1818 for the energy of the bonds broken, and I get 1715 minus, or 1715 for the energy of the bonds formed. I have to subtract them two. So 1818 minus 1715, I would get 103 positive. So positive 103 kilojoules per mole. And the reason that's delta HF, this reaction happens to be delta HF standard, because as long as we're at 25 degrees Celsius here, right, we know that delta H F standard is 0 and 0 for those two, because there's elements in their standard state. That's how we calculate. Those are the 3 ways to calculate delta H. Hess's law, standard enthalpies of formation, products minus reactants, and bond energies, bonds broken minus bonds formed. That is enthalpy. The next video will be calculating enthalpy, all examples of Q and delta H, calculating it and whatnot, and how we're going to go through that. So we'll see you then. Take care, guys.